All right. Good afternoon, everyone. I'm Dave Broadbent, the Education Director with ABYC. And the other guy you see on the screen is Mike Bonicker, our lead instructor. He'll give you a little rundown about his background a bit when he takes over. But I want to thank you all for being here. Good morning to you West Coast folks, and good afternoon to you East Coast guys. This is our second webinar in this series. We're going to kind of try to do these every Thursday. This one's going into some of the electrical concepts. Before we get started, I want to go over a little housekeeping as well as a couple other things. So, you go next slide for me, Mike. So, as everyone's dealing with this COVID-19 issue, it's affecting us also. So, we are all currently working from home. We're working really hard to come up with some great resources for all you out there, training-wise. If the school coming up with resources to help them in these times, we're really committed to our members and doing the best we can for you. So, if you have any recommendations or anything we could do, feel free to reach out to us. Like I mentioned, we are doing these weekly webinars. If you can't make it, they are being recorded, and they are going to be put up on our YouTube page. So, and you will get CEUs for these as participating. So we're going to pull that list and be able to do that for you. Next slide for me, Mike. Okay. So a little bit about what else we have currently that we can offer. So we got a ton of online education things we've been building up over the past couple of years, and most recently, we released our ABYC Standards certification online. So if you've ever wanted to get the standard cert, we actually have a whole module-based training program you can go through, and then we have a self-proctored exam, which is a little bit below that, where you're looking at the Proctor U, where you can actually take your exam at home for any of our certifications. So if you're looking to self-study and looking to advance your education now, there's an opportunity on that. We do have our curriculum and resources for teachers between our digital resources, PowerPoints, and whatnot. So if you know any schools who may be interested, let us know on that end. We also have other online learning courses you'll see. Our free micro courses we put out, as well as our basic electrical and corrosion mitigation course is on sale right now. It's a really great basic course for an entry-level tech to really get a good understanding of electrical and corrosion. So feel free to look at those resources. The email that will go out at the end of this will have links to all those resources, as well as my email address and Mike's for any questions you may have. As far as questions go throughout this, we have 500 people registered for this. If you have any questions as we go through this, there's a little question box. Type it in there. I'll be tallying those up, and at the end, after Mike's presentation, we'll get to as many of those questions as we can. If we don't get to your question, you'll have our email addresses. Please feel free to reach out. And other than that, Mike, I think we're good to go. So I'm going to jump off my cam here and get rolling.
All right, great. Thanks, Dave. All right, everybody. Welcome again to ABYC's episode 2 in our free webinar series. As Dave said, my name is Mike Bonicker. I am ABYC's lead instructor. Been with them for a short period of time now, but spent 20 years on the front lines in a boatyard in Baltimore, both as a tech and as a production manager. So I've seen a fair amount, and I think some of my expertise will hopefully show and be able to answer any questions that you might have. But again, we do really appreciate you signing up for this webinar. Something we plan to keep going for the foreseeable future while things are the way that they are. And we'll do what we can to keep getting content out to you. So what we're going to cover today, and we're going to stay on the basics, and even the basics of some more not real in-depth topics, but some popular topics that are questioned sometime. Wire sizing and voltage drop, how we go about figuring that. Overcurrent protection, the rules that go along with that, and last but not least, battery switches, and what standards and topics pertain to those as well. So should be about a half an hour, maybe a little bit longer. We're going to throw a lot of information in here, but make notes of anything you have questions about. And like Dave said, go ahead and type those in as we go along, and we'll get to as many as we can live at the end, and then you'll have our contact information if you need to contact us later. So I'm going to drop off my picture now so you get a better look at the presentation, and we'll get started. All right, so we're going to start at the beginning with our fairly famous ABYC depiction of the Ohms guys. These guys represent the three primary components or principles of the electricity that we deal with. We have volts, we have ohms, and we have amps. So you can consider electricity in a very basic way in terms of water in a hose. The voltage is the pressure, sometimes referred to it as the potential. The amps, you can think of that as the rate of flow, and the resistance is the factors that are trying to slow down that rate of flow. The resistance is our ohm specification. So that, it also, this diagram also depicts how these three entities interact with each other. You have the volts trying to push the amperage through the wire, and the ohms there, the resistance, any place there is resistance is going to slow that ohms down through its travel. So our relationship between those three entities, resistance in ohms, current in amps, and voltage in volts, of course, there are mathematical certainties. If resistance increases, the current decreases. If voltage increases, there's going to be an increase in current flow. These are givens. In all circuits, voltage is lost as it travels through the circuit. And all of these relationships are examples of what is known as Ohm's Law. So we're not going to get into the specific deep theory here, but Ohm's Law and the power equation, which we're also going to discuss in a second, very useful tools, mainly to understand the relationship of how one of these aspects affects the other. Ohm's Law states that if you know any two of those three values, you can always calculate the third by multiplying or dividing. So simple terms, to find out voltage, you multiply amps times resistance, ohms. If you want to find out amps, you divide volts by resistance, or if you want to find out the resistance, you divide volts by amps. Now, Ohm's Law doesn't come into play in your everyday mathematical troubleshooting or installation work. Again, it more gives you an idea of what the relationship is between those three entities. So as an example, we normally have 12 volts in a system. If we can measure the current, the amperage flow at 4 amps, divide the volts by the amps, and we get 3 ohms of resistance. Conversely, if we know that the voltage is 12 and the resistance is 3, we get 4 amps. Very easy mathematical equations to see how those entities affect one another. The power equation is a much more useful equation information on a daily basis, on a regular basis, for things you need to figure out in your electrical meanderings. The power equation expresses the relationship among potential, again, volts, current, and amperage. And this time, instead of resistance, we're putting in power factor, which is measured in watts. Equation works exactly the same way as Ohm's Law. If you're given any two, you can measure 2, you can find out the third. So to find out the power, the watts, multiply volts times amps. If you want to know the voltage, divide watts by amps. If you want to know amperage, divide the watts by volts. This equation is very useful because the ABYC standard E11 requires all manufacturers to label their equipment with values for potential voltage and current or power. So on this microwave label, power is listed at 1.2 kilowatts and the voltage is 120 volts. To find the current, we're looking for the amperage. We're going to convert that 1.2 kilowatts to 1200 watts. 1000 kilowatts is 1 watt. So 1200 watts, sorry, other way around, 1 kilowatt, 1000 watts. Then divide the 1200 watts by 120 volts, and that tells us we have a 10 amp draw from the microwave. It's very easy to do, and that's again, practical application when you need to figure out overcurrent protection or wire sizing for an appliance, for any component. If you're not given what the amperage draw is, that's how you can figure out what you need to deal with. And there should always be at least 2 of those needed values listed on any equipment, AC or DC. But before applying the power equation, we want to important to determine factors such as the correct wire size, and the rating for overcurrent protective devices. So that brings us to our trivia question of the day that has a prize. We want to know what is the main thing that the terms volts, amps, ohms, and watts all have in common. You can all put in answers, all the correct answers we get. One person will be chosen from those correct answers, and you receive a spiffy new ABYC t-shirt. So give it your best shot. And again, this is going to be recorded later, so this only pertains to the live broadcast.
And Mike, just to jump in, yeah, you can put your questions, if you're going to answer that, put it right in the question column, and I'll be compiling that. And like I said, we'll pull a name from the hat of the right answers.
All right, great, Dave, thanks. So let's move a little further into the complexity of our electrical systems and identify the components that we have in our electrical circuits. We're going to have a power source. In this drawing, it's a battery. In AC, it's going to be our shore power. We have our conductors, which is our wiring connecting all of our components. We've got an overcurrent protection device, hopefully, if it's installed correctly to ABYC standards, which is our circuit breaker or fuses. We've got a switch to control the load, which sometimes can just be that breaker if it is a switchable breaker. And we have the load, in this case, a cabin light. The cabin light, the load is the resistance in the circuit. It's our component that the circuit is there to provide power to. And at the end, we've got to have a return path to ground. If we do not have that return path to ground, nothing is going to work. In order for current to flow, you have to have a complete circuit. So proper conductor sizing is important for several reasons. We need to ensure that we're not going to exceed the wire's thermal limit that it's rated for, that it can adequately handle the amperage draw requirement that we're going to ask it to handle. And for DC conductors, that wire does not exceed the voltage drop limits prescribed in standard E11, which we will address shortly. So in sizing AC wire, we're going to use one of several tables found within standard E11. There are this one, table 3.7, which gives us the maximum allowable amperage of a single AC, and in this case also DC conductor that is not bundled, sheathed, or in a conduit. Table 3.8 gives us allowable amperages when we have up to 3 current carrying conductors that are bundled, sheathed, or in a conduit. There are 3 additional tables, which you don't necessarily have to worry about, just to understand that they're there and why they're being mentioned. They further derate the current carrying capacity of AC wiring, but they no longer apply to DC conductors. It is felt that there is sufficient derating of our DC conductor ampacities through table 3.8, which is for 3 current carrying conductors, even if we add further wires to that bundle. And what we're going to look at here, I want to just take notice. If you get my pointer. So this is for single conductor. So if we look at 10 gauge and we go over to the 105C column. Now, whenever you reference this, you will normally be referencing the 105C. That is the conductor insulation rating. And all marine cable, basically all marine cable, if you're buying the right stuff, is rated for 105C. Per the standards, 60C is for outside engine spaces, which is why it says it's not permitted for inside engine spaces. And 75C is the minimum for inside engine spaces. But if you buy proper marine cable, it will almost always be rated at 105C. So our 10 gauge wire, we come over to 105C. Outside an engine space says we can put 60 amps through that piece of 10 gauge wire. Inside an engine space, we can put 51 amps through that piece of wire. If we go to table 3.8, which is for up to 3 current carrying conductors, use our same 10 gauge, go over to the 105C cable. Now you can see, because we've added 2 other current carrying conductors, we're now only allowed to put 42 amps instead of 60 through the wire in outside engine spaces, and only 35 amps inside engine spaces. So as you can imagine, those subsequent tables that I mentioned, the more you add together, the lower this number is going to go for the amount of amperage that you can run through that wire, with it being included with many other cables. So when we use the derating cables, the current carrying conductors that they're talking about, we do not count the grounding conductor. We do not count the green because it is normally not current carrying and therefore will normally not generate any heat. The main points to consider are whether or not the wire run goes through an engine room space, what the engine insulation temperature rating and the amperage handling requirements are. If any part of that wire run goes through an engine space, it has to be rated to the lower engine space rating. If you run from one end of the boat to the other and it's only in the engine space for a third of that length, you've got to rate it for the engine space rating. A voltage drop. Voltage drop is mainly a DC issue, which we'll see. As we mentioned before, in all circuits, some voltage is lost as it travels through the circuit and is referred to simply as voltage drop. For AC conductors, we are concerned mostly about heat buildup, and that is the crux of our derating system for the conductors based on the wire itself and how many wires are bundled together. In our applications, voltage drop is not considered with AC because the length of the wire runs for AC circuits found on typical boats is not considered long enough to be a significant factor for performance. It does occur with AC voltage over much longer distances, but due to the higher potentials voltages that we're dealing with, 120, 240, even 480, it is not a concern for wire runs of less than 100 feet. So anytime you hear voltage drop, in our world, the marine world, you're talking about DC cabling. So for DC cabling, due to the fact that we have a comparatively low potential, our voltages are much lower. We're 12, 24 most of the time. We've got to consider the following: what that nominal voltage is for the circuit in question, the amount of amperage that we're asking the circuit to deal with, and the total length of the circuit. So we have voltage drop tables to deal with this issue. And these voltage drop tables are specified for either 3% voltage drop or 10% maximum voltage drop, and that depends upon the nature of the circuit. It is very important to remember that when figuring the total circuit length, the distance is from the source of power to the load in question, your device, and back to the source of power. You've got to consider that to establish the total length of the circuit. The length of the circuit is not the distance from the battery to the light or the AC panel to whatever it goes to. It's twice that distance. You've got to calculate the entire loop, the entire circuit is the total circuit length. So conductors that are used for panel board or switchboard feeders, bilge blowers, electronic equipment, navigation lights, and other circuits where voltage drop has got to be kept to a minimum, that wire shall be sized for a voltage drop not to exceed 3%. And we'll see in a minute what size wire we're talking about here to be able to accommodate that. Conductors used for lighting other than nav lights and other circuits where voltage drop is not critical shall be sized for a voltage drop not to exceed 10%. So even in the cases we're not trying to hold that voltage drop to 3% for critical items, we don't want it to go over 10%. 10% voltage drop for most electrical items is going to be an issue. It's just not going to work right. So for our cabin lights, fans, pumps, windlass, all ancillary DC equipment, 10% is the most we want to see on that wire. So on the tables themselves, the circuit lengths are given across the top of the table in feet, but they're only given in 10-foot increments beyond 30 feet. So if the length of the circuit you're dealing with is in between any of those numbers, always go to the next highest number. Use the next highest number as your reference. On the left-hand side of the column, the amperage values are listed, and they're given in 5 amp increments up to 30, and then also in 10 amp increments. So if your amperage falls between some of those, one of those, or two of those, sorry, numbers, you've got to go to the next highest one as your reference point. So in using the voltage drop table, the first thing you need to do is determine what kind of circuit you're working with. Do I need a 3% voltage drop or 10% voltage drop? And then you reference either the 3% or 10% volt drop table. So determine your actual wire length, the actual wire length from the source of power to the device and back. Assign that value to the next highest distance given in feet across the top of the row of the table if it doesn't match one exactly or very closely, within 1 foot. So use your amperage, the amperage that you need to deal with, and is given on the left-hand side of the column. And then again, use the next highest number to your actual value if you're in between numbers. So you want to slide across the page from your amperage number across to below your distance number. And the number you land on for proper wire gauge is going to be the proper wire gauge for that circuit. So on our 3% table, let's just deal with 20 amps. So 20 amps, and say we've got a 50 amp circuit. That's 25 feet and 25 feet back. For 20 amps on 50 feet for a 3% volt drop, we've got to use a piece of number 4 cable. That's a fairly substantial piece of cable. Compared to our 10% volt drop table, 20 amps, 50 feet, we only need a piece of number 10. So you can see there is quite a sizable difference in wiring between 3% and 10%. Conductors introduce electrical resistance. So some voltage drop is inevitable. We can't have zero voltage drop, but 3% is pretty close. General rule is amperage and wire length increase, so much the wire size. As you're using these tables, keep in mind, if you're not terribly familiar with wire gauges, the higher the wire gauge number, the smaller the diameter. There's an inverse relationship. So we can see our 14 gauge, high number, very small cable. 1 gauge, low number, very big cable. In the second column, we have 0 gauge, which is sometimes referred to as 1/0. Then we have 0 gauge, which can be written as 2 zeros or 2/0, 2/0, and then 3/0 and 4/0. 4/0 is on the large side of what we typically run into in our DC cabling, but you can go larger than that with the circular mill cable if necessary. So overcurrent protection devices for our wire that we just hopefully sized properly. Some examples of what they are, and the basic rule that our overcurrent protection devices need to be located within 7 inches of the power source. That applies to AC and DC. It's mostly a DC concern, and I'll bring up where it falls in AC most of the time. But it applies to both equally. If it's not physically or practically possible to get it within 7 inches, then we have what we refer to as the 740/72 inch rule, and really it's exceptions to the 7-inch rule. So here's a diagram, fairly simple system and a little bit more complex system with 2 batteries. So our main standard says we want that overcurrent protection within 7 inches of the source of power. In this case, we're dealing with a battery. So for wires connected directly to a battery, our exception is 72 inches. And that's the only place we get a 72-inch exception is at a battery, anything connected directly to a battery. So if we can't get that within 7 inches from the battery, we have up to 72 inches to get that overcurrent protection in. From any other source other than a battery, if we can't make 7 inches, we have 40 inches to get that overcurrent protection in. And you can see we've got 2 connections here to the battery, one from the unswitched, the battery side of the battery, one from the switch side of the battery, and even one coming off the starter post, which is not ideal, but I suppose it could be used as a source of power. Over in our little bit more complicated, no difference there. Again, only the wires that are connected directly to a battery are allowed that 72-inch maximum distance on our overcurrent protection. Everything else has got to be within 40 inches. And what makes that exception possible is that we have to protect this section of the wire with some sort of loom, some sort of covering to physically protect that wire from being damaged from the source of power to where it connects to the overcurrent protection device. In all these scenarios, that piece of wire between the connection and the overcurrent protection device has got to be in a piece of a sheathing of some sort. So to reiterate, the battery is the only connection that has a 72-inch exception. AC circuits have no 72-inch exception. 40-inch rule applies to overcurrent protection at sources of power other than a battery. And again, it's not 7 or 40 or 7 or 72. It's 7 or inside those long ranges. The intent is still to get that overcurrent protection as close to the source of power as possible. And the exceptions are only allowed if the wire receiving overcurrent protection is physically protected by a sheath or enclosure from the source of power to the overcurrent protection device. That sheathing is defined in ABYC Standards as a material used as a continuous protective covering, such as overlapping electrical tape, probably the least preferable of all the options. Woven sleeving, molded rubber, molded plastic loom, or flexible tubing around one or more insulated conductors. So that's the kind of material we need to see around those conductors if you don't get that overcurrent protection within 7 inches. There is one exception. All electrical circuits are required to have overcurrent protection installed except for engine starter cranking motor circuits. They do not need overcurrent protection. There are some strict guidelines as to these circuits that, if done properly, will minimize or eliminate the possibility of a short circuit. They're there to eliminate damage to that piece of wire because we're not putting overcurrent protection in. Well, the first thing that's got to be done, because we're not putting any overcurrent protection, it's got to be, again, in a sheath of some sort. But also in the standards, E11-14422 starts with battery cables that don't have overcurrent protection shall comply with the following. They shall be routed above the normal bilge water levels throughout their length. This is positive and negative. Battery cables shall be routed to avoid contact with all metallic fuel system components. And the ungrounded positive battery cable shall be routed to avoid contact with any part of the engine or drivetrain. That positive cable is not to be secured to the engine at any point other than the starter post. Although it's not required, as we discussed in recent years, some builders have started using appropriately rated breakers in their starter circuits. If you can do it practically, it's a good idea. There's no reason not to do it. It's just not required. That's because starter current draw has gone down because of better design characteristics of the starter motors, and it makes the use of circuit breakers for those circuits more affordable. That's mainly the issue as to why they're not required, is because coming up with an available breaker or fuse that will survive the current inrush of a starter is not practical in almost all applications. We'll talk a little bit later about battery switches and inrush current as far as ratings, and they'll survive an inrush current, but a fuse is a fuse. Depending on its personality, breaker, it's going to trip on that inrush current and never give you a chance. So if you've got a starter that has a low enough draw and you can put a proper size breaker in there that doesn't cost $1,000, you're probably right in wanting to do that. There is some confusion that can occur when your power supply is feeding both a starter motor circuit, which is not required to have overcurrent protection, and it branches off to supply the DC panel or other things. So in our drawing here, which is the same as the other, you can see this circuit, the heavy black wire circuit, is our cranking circuit and does not need overcurrent protection. And if you put overcurrent protection in there, trying to protect this, it's going to trip every time you start the engine. So in this case, you're allowed to use the battery switch connection as your source of power to feed. And now this is on the unswitched side. You're going to be on the switch side, more than likely feeding your panel. You can use this as your source of power. Then you either have 7 or 40 inches to get your proper overcurrent protection in just for that auxiliary circuit, whatever it may be. In most cases, again, our intent is still to get that overcurrent protection as close to the battery as possible. In a case where you have a separate battery for your house loads, that's not an engine starting battery, we like to see that overcurrent protection before the switch. The idea is if you have a place where you can get a switch in, you can get overcurrent protection there. And we'd much rather have the overcurrent protection first versus the switch. In this case, because of this circuit, you basically have 2 separate circuits coming off the same power source. You can have the switch here and then come off of that switch with the properly rated fuses for your auxiliary loads. The type of circuit breakers recommended by ABYC is what's called a trip-free circuit breaker. Trip-free circuit breaker is defined in the standards as a resettable overcurrent protection device designed so that the means of resetting cannot override the current interrupting mechanism. This means that you cannot hold the breaker in position if a fault still occurs. Any of you with experience with these breakers will know they will not reset to any extent when you try to push the breaker back over to reset it if the fault still exists. And again, in all cases, everything we use, you should always use marine grade products. As far as breakers, even if you do hopefully use marine grade products, they are not serviceable devices. If they fail, they've got to be matched and matched to the specifics of the circuit. Don't assume that it was right in the first place. Make sure you know what that thing is powering, what it should be. It may be correct, it may not be correct, but don't put the same breaker back just because that's the size that was there. Confirm what that circuit actually is. But you've got to replace it. Do not attempt to repair circuit breakers. One practical topic while we're sort of in that realm is on AC and DC panels. They are allowed to be in combination panel, but the back of the AC section of that panel has got to be covered with a cover that needs tools to remove it so that those AC components cannot be accidentally contacted if someone's working on the DC side. That is an ABYC standard. One very specific subject related to overcurrent protection is what's called a locked rotor concern. Basic rules of our overcurrent protection is that they be no more than 150%, rated at no more than 150% of the ampacity of the wire that you're trying to protect. Again, we are trying to protect the wire with our overcurrent protection. Just like your house, you have wiring in your house that goes to a plug. It's got a 15 amp breaker in the panel. They don't really care what you plug into that plug. If it's too much, it's going to trip the breaker. Essentially, the same thought in both. So we're trying to keep that length of wire from burning up. That's our main concern, is to eliminate how much wire can burn up in that boat if something goes wrong. The reason we allow that 150% of the rating of the wire is to allow for rounding up of overcurrent protection devices, fuses and breaker ratings, which are generally available in 5 and 10 amp increments. And the higher you get, the further apart the increments are. At the low end, where we're talking about here, fuses are available in 1 amp increments and even less, which is very important. In the case of a motor circuit, an exception to that 150% rule exists, and it's because of this concern known as locked rotor. A locked rotor is a motor that's trying to turn, but due to a shaft bearing seizure, a piece of debris wedged in a bilge pump impeller or a fan blade, the motor can't turn. In this case, the motor is going to initially try to start up. Which if you had a clamp meter on the wiring, you would see an initial spike in the amperage draw. But that draw is almost immediately going to exhibit a decrease in current flow. That decrease brings the current draw lower than the ampacity of our conductor and obviously lower than the overcurrent protection if we rated it at 150% of the conductor. Neither of those are going to be affected, and the current's still going to flow, and the motor is going to start to heat up. Heat buildup in the motor is going to add to the problem because it's increasing the overall electrical resistance in the case as it gets hotter. And because of this, if the fuse of the breaker that's serving that motor is rated at even as little as 1 amp more than the manufacturer's recommended level for that motor, it's not going to blow, and the current will continue to flow until the motor literally burns up, potentially causing a fire on board. The manufacturers of motor devices are required to provide what the overcurrent protection level must be for that device in order for it to trip properly. Battery switches. So we need a way to control one of our other components in our circuit. And a lot of people question when you don't need a battery switch. Well, it's spelled out pretty plainly in E11. A battery switch shall be installed in the positive conductor from each battery or battery bank with a CCA rating greater than 800 amps or 100 amp hours. If you can't or don't know the CCAs. Now, 800 amp hours is not a lot, and 800 amps is not a lot. You can get maybe a group 24 battery that does not have 800 amps, but you can get to group 24s that have 800. And if you go to a group 27, group 31, you're definitely going to be higher than 800 amps. So in most all cases, you're going to be required to have a battery switch, a main disconnect in that DC circuit. And even if it's not required, if it's possible, it's a very good idea, especially for servicing considerations, not to mention safety considerations. You can have conductors supplying certain things that are connected to the battery side of the switch, the unswitched side of the switch. Any electronic equipment with continuously powered memory can be connected there. Safety equipment, bilge pumps, alarms, carbon monoxide detectors, and bilge blowers. And any battery charging. If you have an output from your battery charger, instead of taking it all the way back to the battery, if that's not practical, you can attach it to the unswitched side of that switch, so it is basically connected directly to the battery through the cable between the battery and the switch itself. And as you can see there in our depiction, there's a bilge pump float switch. If you do attach things there, that is where your overcurrent protection has got to go. As far as battery switch locations, there are standards that apply to that. Specifically, a battery switch shall be mounted in a readily accessible location as close as practical to the battery. As close as practical, but if given a choice, we don't necessarily like to see them in the engine room. I know that's hard to accommodate sometimes, but we don't necessarily want to go into the engine room to shut off the battery switches to stop an electrical fire that's in the engine room. Access to a switch shutoff should be outside of machinery spaces. You can accomplish that by using basically a solenoid switch, a high current latching contactor that's mounted close to the battery but has a remote switch safely located outside that space. With that system, the remote switch can be placed in an easily accessible location while the actual switch is close to the battery where we like to see it. Further advantage of that type of configuration is that it allows a significant reduction of expensive heavy gauge cable. Also helps to reduce weight. You're not running big cables from the battery to a battery switch that's somewhere remote and back to the source. It's certainly a much cleaner way to go, and it gets you that battery switch in a place where you can shut it off without having to gain access to a machinery space where there's a good chance the problem might be. So here we are at our ratings, which I mentioned earlier. So the cranking starting rating of a battery switch shall not be less than the maximum cranking current of the largest engine cranking motor that it serves. The minimum continuous rating of the battery switch shall be the total of the ampacities of the main overcurrent protection devices connected to the battery switch. Means like our or situation where you have one battery and overcurrent coming off and circuit going to the panel or whatever else. That switch has got to be rated to handle the capacity of both of those, or the ampacity of the feeder cable to the switch, from the battery to the switch, whichever is less. So they have intermittent and continuous ratings. The biggest issue with switches is for cranking circuits and the inrush current that is associated with starter motors. The inrush current is going to, more often than not, far exceed the actual switch's intermittent rating. In those cases, you're going to use the actual cranking current as the intermittent load when determining a properly rated switch. That momentary inrush, is not enough to damage the switch. But again, as we discussed before, it is enough to trip to blow a fuse. So in this case, we're worried about the actual cranking current. That's the current that may flow for 2, 5, 10 seconds in hard starting circumstances, and that's what we want to rate that switch to. And so some final notes on battery switch connections. There are some manufacturers that provide specs for using a torque wrench to tighten those lug connections. You've got to make sure that they are secure. A loose connection is going to generate considerable heat, and heat is the main result of resistance. It could damage the switch. I've seen switches where the switches got so hot that the studs molded into the plastic switch just popped out because it turned to gel. Connections to those switches to be solid. We're talking about an area where there's a very high current flow, very big cable, and any loose connections there are going to have some pretty dire circumstances. So make sure that those battery switch connections are very secure. And that's it.
All right, Mike. Well, we do have some questions here. Feel free. We do have some time left here, so you guys want to keep asking some questions. You can type them in, and I'll start reading some of these off to Mike. Is there a reason why bilge pumps are not considered critical equipment?
Yes. Let me see if I can get my camera back on here. The intention of a bilge pump is to remove normal accumulations of bilge water from minimal leaks and rainwater. Bilge pumps, believe it or not, are not intended to keep boats afloat. That is not their purpose. If you have a crash pump, if you have an emergency pump, that is the purpose of that. But bilge pumps are intended to remove the normal, their intention is for the removal of normal accumulations of bilge water, not emergency removal.
All right. Get to another question here. To go through all these trivia answers, we've had 30 or 40. Why bother to mention the 7-inch rule if you can go to 72 or 40?
Because under circuit, again, the intent is to get that overcurrent protection device as close as you possibly can. I would not profess to know how they came up with 7 inches. Sometimes that is possible. Many times it is not. Mainly that's the most amount of wire that they want unprotected without some sort of a sheath on it before overcurrent protection device. So it's there, but you've got the other parameters as long as you cover the wire. And one thing I don't think I did mention was where that overcurrent protection length comes into play in AC the most. It comes into play for output breakers on generators that don't have them. Gen sets that are required to have, if they are not self-limiting and required to have some sort of overcurrent protection on the output, that is normally where that 7 or 40-inch rule comes into place for putting overcurrent protection in a box as close to the generator as you can get it.
All right, the next question is, how do you address the covering for AC on AC and DC combined panels on older vessels?
There are many, there are options. There are some pre-made covers for the back of panels. One thing I've found that actually works pretty well are the small plastic, blown plastic. They're normally black. I'd call them plenum boxes for AC, air-conditioned systems. They normally don't have any holes in them. They're easy to cut. They come in a bunch of different sizes and they work very well, but there are some special made covers you can use at a minimum. I've seen people use standoffs with a piece of plexiglass. You have a through bolted standoff through the face of the panel that you can put a piece of plexiglass over that back to try to meet that the intent of that standard as well as possible.
All right, we got a handful of questions on the availability of the presentation and whatnot. If you had any audio issues, next time you jump in, try calling the call-in number instead of just computer audio. Sometimes, depending on where you are, it can be a little funky there. But as far as recording, it will be on our YouTube page. So tomorrow you'll get a follow-up email from this, and it will have a link to our YouTube page so you can watch it there. Next question for you, Mike. How do we size a wire for a starter motor of unknown cranking amps?
That's not a straightforward proposition. What I would do, depending on the size of the engine, if it's a 3 or 4 cylinder engine, I would probably use a piece of 2-aught to be on the safe side. Connect it to a battery and get yourself an amp clamp that you can clamp on that wire and crank that motor over. You don't even have to hook it up to, if it's something that's on the bench, as long as you can crank it. The starter's got to be on the engine, obviously, and see what kind of current flow you've got there. There's very few, I would imagine, unless it's extremely old, in which case you probably ought to replace it anyway, that a manufacturer that you can't get either specifically what that starter is rated for, or from the engine manufacturer who can't tell you what that starter should be rated
for. All right. Does heat shrink tubing count as sheathing for wires?
No, it does not. Because it has, in general, your sheathing is continuous length for a fairly long piece of wire. So I know you can buy heat shrink tube in a decent length, but it's not normally used that way.
All right.
One thing I will say about sheathing is that if you're running wire that's DC in duplex wire or AC that's in triplex wire, the white cover that comes on that constitutes sheathing. So you do not need any further sheathing on that wire to meet those rules. If it's in the white case, if you've got 2 wires in a white cover, 3 wires in a white cover, that white cover counts as a sheath.
All right. Is a battery switch damaged if the position is changed from 1 to 2 when the boat is underway by the engine?
It could be. In most cases, most all cases that I know of, DC battery switches are make before break switches, which means they contact the new switch position before they break the old switch position, which is in reverse of our AC circuits, where we want to break the existing power source before we make the second power source. In DC, it's a make before break situation. In most cases, it probably would not. You certainly don't want to switch a battery switch off with the engine running. That'll give the alternator some issues. But switching between batteries, as long as it's a normal marine battery switch, it should make the next connection before it breaks any connections. So theoretically, it should be all right.
Got a question about the reel collection behind you, but I think we'll save that for another webinar. So could you comment on polarity of some contactors and breakers? Is it only related to presence of magnetic blowouts?
I'm not sure I understand that question. Read it again for me.
Could you comment on polarity of some contactors and breakers? Is it only related to presence of magnetic blowouts?
In general, because you're seeing DC, and I'm not going to profess to be an expert on this part as far as contactors, I would not think, and I think they are normally marked like a solenoid contactor. If that's what you're talking about. You have two control wires coming in, positive and negative. As long as you make a circuit there, I don't believe polarity matters, but I could be wrong on that. And you just have a switch, two wires that you're creating a switch on the high current side of that. But on the low current side, I would certainly observe any polarity indicators that are on those switches. There's no reason not to.
Right. If a cable is rated for a max temperature, why the difference between inside and outside an engine space?
Because of the ambient temperature that we expect to see inside an operating engine room. It's going to be higher in almost all cases. So we've got to compensate for the fact that that ambient temperature is going to be higher to start with in an engine room than outside an engine room. Just gives you a little more leeway if you are running a wire that's not in an engine room anywhere. It gives you more capability amperage-wise.
All right. And we got a couple here that are a little in depth. I'll save them for you, Mike, and we can shoot some emails out.
Yeah, that's fine.
It's a little hard to address here. Let's see if we got anything new. All right. Is there a recommendation or rule of not using light type insulated cable lugs instead of heavy type lugs for large cross sections where no vibration resistance is needed?
One more time.
Is there a recommendation or a rule of not using light, in quotation, type insulated cable lugs instead of heavy type lugs for larger cross-section where no vibration resistance is needed?
No, there's no standards or recommendations there specifically.
Yeah, I think that kind of that takes us through the majority of the question here. Like we said, if you have a really in-depth question, our emails are out there. You'll get a follow-up email with that. In your original registration email, you have my email, you have Mike's. So feel free to shoot us a note, and we'll gladly answer those. Other than that, I think we had another successful week. We have about 350, 400 people here. We really appreciate you guys coming out. I'll say hi to you one more time on our way out here. So really appreciate you guys all coming out again. We're going to be doing these every Thursday. I think we put the registration out on Wednesday to register for it. If it's full, don't worry about it. It's going to be posted tomorrow on our YouTube page, and you can rewatch it. If you're an educator, feel free to share it with all your students, the YouTube link, and any topics, anything you think you'd like to see, shoot us a note, and we'll try to get one done for you. So with that said, Mike, I think we're good here. Thanks, everyone, again. And
thanks, Dave. Thanks, everyone. Maybe see you in person one day.
Yeah, when this is over. Thanks, everyone.